Okay, nice. So we're going to start again. So firstly, I've just got the rocket back, and I think there's not enough fuel to go into orbit. So we're going to pass this around once again. We're waiting for you. Okay, so now we'll move on to Camille Pirat. So Camille also recently finished his PhD and works for the Swiss Space Center. So despite his Swiss accent, he's going to try and explain the mysteries of space rendezvous and docking. So to show us that his thesis is actually quite trivial.
It
right?
is.
It is.
Yeah.
A round of applause for Camille.
Is it working? Yep. All right. Hello, everybody. Good evening. So we'll talk about space rendezvous and docking. Now that you had a few beers, it will be easier, I'm sure. This picture on the left is one of my favorite ones because, so this is the International Space Station, okay, everybody knows that. But this is one of the rarest pictures where you can see all the spacecrafts which were capable of autonomously docking to the ISS. So you have here the space shuttle. On this part, you have the autonomous transfer vehicle, which is a European Space Agency vehicle, a cargo vehicle. You have a bigger overview of this spacecraft here. And here and there, if I'm not checking too much, you have a Soyuz and a Progress vehicle. At the time this picture was taken, these four vehicles were the only one capable of docking to the ISS. Now, if you wanted to be precise, you would have to add the Crew Dragon vehicle from SpaceX. But at that time, they are all here. So rendezvous and docking was first mentioned by Mr. Obert in 1923, who some consider as the father of multi-staging rockets. And at his time, in 1923, it was really believed that rendezvous and docking was science fiction, too hard to accomplish. He was foreseeing an application such as on-orbit refueling, but it was just too complicated to achieve. It was so complicated to achieve that at the beginning of the Apollo program, the scenario they wanted to do was something like Tintin, which is called a direct ascent, direct moon ascent, where you land on the moon with a spaceship, and you will leave the moon with that very same spaceship without leaving anything behind. Hergé did that in 1954. What is funny is that there is a small company in the US which is foreseeing that direct ascent from Mars using the big big Falcon rocket. So that was presented at the IAC in 2016. So we'll see in the future if this is, this is now clearly science fiction, but we'll see if it becomes reality. So this is the rendezvous, the mission profile we all know from the Apollo mission, despite the funny figure it prints. I'm not sure NASA was aware of that at that time. If we have something like that today, it's because there is one guy, which is called John Houbolt, who fought, so this is this guy, and he was really fighting, and he bypassed all his hierarchy at NASA and went to talk directly to Wernher von Braun to convince him that lunar rendezvous and docking was the only possible solution to make the Apollo mission possible. And he did that. He bypassed everybody, and Wernher von Braun believed him. And so this is why we have such a profile. So you have first a docking here where you have the service and crew module separating from the third stage, then making a rotation and docking to the LEM, going to the moon, and after landing on the moon and taking off again, while leaving some part on the moon, they have the famous lunar rendezvous and docking. So now the only thing they had to do to move from science fiction to reality was to demonstrate rendezvous and docking. And that was done in 1966 during the Gemini 8 mission. If you watched the movie, you all know that the pilot was Neil Armstrong. What few of you will know, most probably, is that the guy doing the science behind the rendezvous profile of this mission was another moonwalker, Buzz Aldrin. And he did his PhD at MIT in 1963, and he was working on some fancy guidance techniques for a far-range rendezvous. And so he was really the brain behind this mission, and Armstrong was the pilot. So this was the first ever rendezvous and docking around the Earth. So the Americans won this part of the space race. And the Russians, actually the Soviets, followed a year later in '67. And they performed the first autonomous rendezvous and docking between two Cosmos satellites. And here we already see a difference in paradigm between the Soviets and the Americans. The Soviets, at that time, they were the best in the world in terms of control theory, estimation theory. And so I think they had lots of confidence in doing that automatically. The Americans, they went directly for manned rendezvous and docking. And one of the reasons, which I had discussing with Claude last week, was that at the time of the first astronaut selection, most of them were pilots, military pilots, test pilots. And it's them, so the NASA astronauts, who really pushed to have a manned vehicle to have manual rendezvous and docking. So how it's done nowadays, you have here two examples of two vehicles going to dock to the ISS. On the left side, this is the autonomous transfer vehicle from the European Space Agency. As I said before, a cargo vehicle, so only carrying freights, no human on board. And to control itself, you're ejecting some gases, very hot gases, hydrazine, a nasty chemical. And what is really hard behind rendezvous and docking is that you don't have to control only your position with respect to your target, the International Space Station here. You also have to control your rotation, so you have 6 degrees of freedom. On the right side, you have the Soyuz vehicle carrying on board 3 astronauts or cosmonauts. The Soyuz vehicle is completely autonomous, so as the ATV, by the way. The only difference is that the Soyuz vehicle, it has humans on board. They are capable at any time to manually override the control algorithms in case they would have a failure. So now let's go a bit deeper inside the theory of rendezvous and docking and see a bit how it's done. So after launching from Earth, typically your launcher will put you on an orbit 200 kilometers above the Earth, and you will be on what is called the phasing orbit. The reason of this orbit is that as you are lower, and Florian told you that at the beginning of this evening, if you are closer to the central body, you will spin faster. So after one orbit, this satellite here will be a bit closer, right? At that moment, the only thing you have to do is to increase your altitude to end up just behind, more or less at the same altitude than the ISS, International Space Station. And how it's done? It's done doing some maneuvers, which are essentially close to a Hohmann transfer. So once you're here, you make a first delta V. Delta V is a delta in velocity. You increase your speed, you increase your energy, thus you increase your altitude. Once you're here, you make a second burn, which will increase your altitude. And one full orbit later of this little guy, you will end up more or less at the same place around the Earth. Now, once you're here, either you can continue describing everything relative to the Earth, or you can be a bit smarter than that. And a good reference frame to describe everything is to take a frame which is centered around the International Space Station. So here we're in daylight now again. So here you have the ISS, and here you have that little cargo vehicle which wants to go to dock to it. How we represent that? This way. You have what is called the target, you have the chaser, and we have axes like that. This axis is pointing towards the velocity, this one is pointing towards the Earth. And if you put a spacecraft here, it means it's not moving at all, it's just trailing behind your, the International Space Station, your target. Now, let's see what's happening if you change a bit the velocity of this guy towards the Earth. So you make a little push towards the Earth. You think, okay, I'm on orbit, 0 gravity, fine, I will go down. Well, not at all. You will first go down, but then you will start moving forward until you start going up and then moving backwards. And this is actually what is happening. You can see it here. Wait to be in the out of eclipse. You see that the small vehicle here is just turning around the ISS. So you can already see that it's a bit counterintuitive. And now let's see the case if you want to dock, let's say, here. So you want to dock here. And obviously, human intuition, okay, I need to move in this direction. So let's do it. Let's push forward. What's happening if you push forward? Well, first you go a bit forward, but then you start to go up, and you are actually going backwards. So not the good way to do it. What do you have to do? Well, you have to constantly push down to force actually the satellite to stay on that straight line motion, to go like that. And so to the question, is it difficult? Well, I mean, said like that, it's nothing really difficult, but it's not at all intuitive. And people could do it very good manually. They had to train a lot, but it's possible. So at the end of the phasing, I told you before, you are more or less at the same position than your target vehicle, but it's not that easy. You have to work a bit more. So the numbers are that you arrive more or less 30 kilometers behind, 5 kilometers below your destination point. At that moment, what you want to do is you want to communicate actively with your target. How this is done? Well, you have like some just inter-satellite link, some antennas, and what it will be used for, it will give you a direct interpretation of your relative position with respect to the target. Once you know that, you can actually make much more precise maneuvers. So precise that they will bring you exactly at the same altitude, but 5 kilometers behind. 5 kilometers behind is still too far away, so you do what is called a closing maneuver, which will bring you at 250 meters behind. At that moment, you will wait, typically, such that the crew on board the ISS are awake. You don't want to dock once they are asleep. You want to have the right illumination conditions. You want to be above a ground station, typically, so that you have direct communication with the Earth, that sort of things. Once all these conditions are met, you do what is called a fly around. Typically, if you want to dock here, obviously you need to align yourself, and then you do the final approach. In case you ever have to dock a satellite, this is typically the profile that you should try to follow. Now, keep in mind that this trajectory is what you would see if you were an observer on board the ISS, so you're an astronaut looking out the window. This is a trajectory that you would see that cargo vehicle approaching. Now, if we put it on the other side, if you are on board the vehicle approaching, this is what you will see. So this is the ISS, okay? And here you are on board the Soyuz vehicle. And now we are doing the fly-around maneuver. So what it's doing, it was at the same altitude than the ISS. And now it's just making a maneuver to align itself with the docking port. That very fast spinning antenna here is their navigation solution. So it's just an antenna which, as it's spinning, it's capturing different signals, and then you can have an intuition, a number on how you are relative to the ISS. Now, if you don't mind, I will just move a bit forwards because it's a bit long. So you are aligning yourself, and now you are in that final approach, that straight line, which is not intuitive, remember. Yeah, going. It's quite slow. Everything is very slow in space, so you have to keep your time. And yeah, just a moment before docking, here we are. And you can see here there will be the probe entering the docking. You see it's right in the center. Baf. Exactly at the center. Did you see it? It's quite impressive. And just look at it. It's just incredibly precise. So, now that you know how to dock a satellite, let's just see a bit the numbers that you need to achieve. So these are two docking mechanisms which are still used. I mean, this one is still used on the Soyuz and Progress vehicle. This one was used on the space shuttle. The requirement that you have as a design engineer is that obviously you have to be able to fit a human through it. So the typical size is about 1 meter in diameter. What is the accuracy that you need to have if you are a little piece of software or a human? You need to be better than 10 to 10 centimeters lateral with respect to the target, and relative attitude orientation of 2 to 5 degrees. So this is what you have to achieve. So you can see that now, 50 years after, more than 50 years, the first docking was 50 years after Mr. Obert first thought of it. This is rendezvous and docking is not at all science fiction. But now if we look at today's science fiction, what is it? Well, today's problem is that we are we start to be strongly limited by the volume we can have on the launcher, in the fairing of the launchers. This is the James Webb Space Telescope, which is, what is the launch date now? 21? No, yeah, 22. Okay, it will keep increasing anyway. Look at the mess they have to go through to fit that massive satellite in the Ariane 5 launcher, which is one of the biggest we have, by the way. Like, each time you have one of these mechanisms which is going to deploy something, that's a single point of failure. They have to put massive redundancy to be sure that once it's at 1.5 billion kilometers away from the Earth, you will not just spend a few billions of taxpayer money to waste. So what people start doing, it's to say, okay, why don't we do like the Swedish people do? We do kit furniture, kit satellites, kit telescopes. We send all the pieces stacked on top of each other in a launcher, and then we assemble everything on orbit. And this is what I was doing, investigating during my PhD with the European Space Agency. We wanted to check if CubeSats could be used to build on orbit larger structure, space telescopes, I don't know, radio communication antenna, whatever you want. So CubeSats, just to give you an idea, it's very small. This is the autonomous transfer vehicle. We saw a video about it before, a cargo vehicle. This is a human. This is the ISS. CubeSat, the size we foresee for rendezvous and docking is 30 centimeters. So this is the length of your forearm, which means that you have to adapt everything. Typically, you have to adapt the docking mechanism. So that we did with some students here at EPFL. We achieved a size of 10 centimeters. What precision do we need to dock two pieces which are 10 centimeters across? We need to be better than 5 millimeter relative positioning and better than 1 degree. And then, of course, we had to check that it was possible to do. So here, the red circle is the 5 millimeter requirement. Here, the red circle is the 1 degree requirement. And we did some Monte Carlo simulation, so roll the dice. And you can see that, well, we have quite some margins with respect to our requirements, which gives confidence that once you're in orbit and that you will realize that you forgot so many stuff, well, there is still a good chance that it will dock. To give you an idea on the speeds we are talking about, this is a docking sequence in real time. So the docking speed is about 1 centimeter per second. So when I was saying it's slow, like it's really slow. If we're going to the end, I would lose everybody here in the room. That's why I'm not going to do that. I'm going to finish now. Thanks a lot for listening to me, and I'll be happy to answer your questions. Thank you.